So one of the introductory slides that I have there was about a climate emergency. You all see the news. You see what happened in the Amazon a couple of years ago. We're still actively having wildfires in California. We have all of these hurricanes that are coming. Thankfully missing Florida, but unfortunate for our other friends around the country and around the world as well. And a lot of what we see in the literature is scientists raising more alarm that this is an emergency. This isn't something like the quote, in the quote that was shared earlier, can be put on for another generation. We're feeling the effects of this now. So for my presentation today, I'm going to try to be good on time. Do I still have 25 minutes, or do you want me to shorten?
I'll give you a little counter.
Okay, thank you. My passion and enthusiasm for this topic, and when I lecture about this in my classes, it takes like a week. So I'm going to shrink it down as best as I can and keep myself on track. But I wanted to talk to you a little bit about natural patterns in climate change, as well as these anthropogenic patterns that we're seeing today. And then try to drive home this aspect that we are in this climate emergency, which probably some of you already agree with. Next. Yeah, my little thingy's not working. And then what are the impacts of anthropogenic climate change on marine systems? I'm going to focus on marine systems because that's my area of expertise. And just try to show you how complicated a lot of these different interactions are. And then I always like to leave with the message of hope, because this is all very overwhelming, and this all feels like a problem that is too big to address. And that's where we lose a lot of people who are on the fence about climate change. They might recognize that this is real and this is happening, but they have lost hope that there is something that we can do about it to address these issues. And so I'll give you some opinions, thoughts on that. I'm not a social scientist, but through my research working with people, I'll leave you with a few opinions and thoughts. So from what we understand about the science of climate change, we know that there are physical, chemical, and biological changes that are happening all throughout the ecosystem. And again, I'm going to focus on the marine ecosystem. So those changes are evident in a variety of research: sea level rise, ocean acidification, warming oceans, changes in ocean circulation, all of these things. I'm going to talk a little bit about them. If there's any one particular topic I don't have time to go into detail about in the discussion, feel free to come up and ask, and there's an encyclopedia up there. So, and all of these things we have to keep in mind are connected through these small little threads that are sometimes invisible and we don't even realize are there until we change one thing and we see those ecosystem cascades that happen. So I like to show this figure. This is from 2017 when we had that unusual cold snap that hit the Northeast. We had those super storms, several feet of snow fell on Washington, D.C. So what this figure shows you in terms of the color changes are the temperature anomalies. So how different was temperature from previous records? So you can see that most of the Northeast of the United States and the East Coast of the US is blue. They're experiencing colder than normal temperatures. Well, when you look globally, you see a lot of red that are experiencing hotter than normal temperatures. And I like to show this figure because when we look at where our laws are made, where are they made? In the areas that are experiencing these abnormal cold elements. So one of the reasons why you see a shift from us calling this global warming to climate change is because climate doesn't change the same everywhere. We're going to have areas that are experiencing colder than normal temperatures because of changes in atmospheric circulation and the circumcurrent polar region. You have these currents that are coming down and bringing that cold Arctic air to the east coast of the United States. Where you have other areas that are experiencing those hotter areas, and even Florida, you can see there was no change. We also have differences that is not shown in this figure with changes in precipitation. We have areas that are experiencing drought, where other areas are seeing increased precipitation. So it's not a uniform change that we're seeing across the globe. And it's very complicated in terms of which areas are going to see which changes. And there's a lot of modelers out there that are looking into that. So I want to talk to you a little bit about natural patterns in Earth's climate. Earth has a historical record going back millions of years, where we can look into the geological record and we can see that we shift from periods of ice age to periods of global warming. And so we have these glacial and what we call interglacial patterns. And we know that those have existed over the history of the world. And those changes occur by natural shifts in things like solar energy, atmospheric circulation, ocean currents. There have even been records of massive volcanic eruptions that have caused many ice ages, a volcanic eruption in Indonesia, causing an ice age in Europe. So there are these things that happen that we know that can shift the entire climate or shift portions of the climate around the world. Now, I'll talk to you a little bit about some of those because they're cool, and I like talking about them. So if you have my click to the next slide. So when we look at what climate change is, we have the most of the energy, the heat from our planet is coming from the sun. There is some geothermal energy that comes up from our core, but most of it is coming from the sun. And that amount of energy that comes from the sun varies quite a bit. And some of those natural phenomena that occur are actually changes in the luminosity of the sun. The sun shifts in its brightness. One of the other things is sunspot activity. This is actually one of our longest sort of visual records of climate change. It started with Galileo when he built his first microscope, and he looked at the sun, because why not? And he noticed that there are these dark patches, these solar spots that were on the sun. And so from that first telescope looking at the sun to today, we monitor those sunspot activity. And what we can do is look at how many sunspots there are and compare that to the temperature of the Earth. And there's actually a correlation. And it's not until really recently that we realized what was going on, but from what they think is that there are basically solar storms that create outgassing, and that can lead to increases in that energy coming to the Earth. And you might hear about that every now and then. We get a solar storm that hits the Earth and we worry about like satellite communications and things like that. So we can relate the presence of these sunspots to what's going on the planet. We also have shifts in the way that Earth rotates and the way that Earth rotates around the sun. These are called Milenkovic cycles. So this is where I like to shake you up your K through 12 education because you learn that Earth rotates around the sun in an ellipse, but not all the time. Sometimes it's a circular orbit. And so when we have more of a circular orbit, that changes how far away we are from the sun, and it increases the amount of solar radiation we receive, and that would be a period of warming. Then we also have the Earth tilting. It's not always at the same degree. It wobbles a little bit. And then the way that the Earth spins like a basketball, it's not a perfect spin. It also wobbles. And so all of those different cycles that our Earth goes through, we know about, we've been able to predict, we've been able to observe, and that is related to changes in climate as well. If we take all of these natural phenomena and we line them up, they match up very well with the geological record. When we go into ice cores, when we look into coral tissue, when we look into tree rings, we can see the relationship between all of these different factors between the glacial and the interglacial periods. So how is what we're experiencing today different than those natural things? So this is a pretty recent paper that's come out. And what you see is the black, the actual observations of the temperature of the Earth. In blue is what percentage of that change is related to these natural phenomena, Milenkovic cycles, luminosity of the sun, solar sun. So if we take what we know is natural and we project that out, how much of our temperature is related to that, it's the blue line. And then we look at the observed, there's a difference, right? And so that difference is the red, which is that anthropogenic, that human-introduced interference in the temperature of the Earth. So we can see how much of what we're seeing is natural and how much of what we're seeing is caused by us. So when energy comes from the sun, there is a certain percentage of it. Do I click? There's that, yeah. So we have 30% of the energy from the sun gets immediately rejected out into space. It bounces off of our clouds, it bounces off of the ice caps and the glaciers, and that gets re-radiated back into space. The other 70% of the energy gets absorbed into the atmosphere, gets absorbed into the plants, into the ocean. And it's that 70% of energy that we're really concerned about. That's what enhances the greenhouse effect. There is a natural greenhouse effect. We want it because we don't want to be like the surface of the moon that doesn't have an atmosphere. We want an atmosphere, we want some greenhouse effect. We just don't want to make it hotter than it should be. So when that 70% stays here, the energy changes because of the extra greenhouse gases in the atmosphere. And then we get this longer period of energy here, and it takes a slower amount of time to re-radiate back out into space. And so that extra heat, that's what we're feeling and experiencing as part of climate change. So what are the human impacts? CO2 is the biggest contributor. That's a very famous graph there from Mauna Loa Research Station in Hawaii. They've been tracking CO2 in the atmosphere since the 1950s. You can see that it just keeps going up and up and up and up and up. And oh, that's okay.
Too fast.
One of the other things I wanted to talk to you about is that there are other greenhouse gases that are out there as well. There's things like methane, chlorofluoric carbons, which are what were stopped with the Montreal Protocol and caused the ozone hole. Those are still in the atmosphere. They are contributing to climate change. We also have things like nitrous oxide, sulfur dioxide, that are all part of this problem. CO2, scientists have measured that it's about 80% of the problem, but with a lot of our reliance on methane and our shale production and methane extraction, about 3% of the methane that they use for those deep drills that they dig in for natural gas releases methane into the atmosphere. So the methane is a growing problem in terms of atmospheric chemicals. So when we look at the concentration of CO2 in the atmosphere, this is an ice core. So they're able to go back 800,000 years using this ice core, just digging down deeper into the layers and measuring different isotopes trapped in the little bubbles when that ice formed up to 800,000 years ago. So when we look at the concentration of CO2 historically, oh, yeah, go back, please. That's okay.
Sometimes we turn, I think.
Yeah, so this right here is the historic levels of CO2 that we can measure directly from those little bubbles in the ice cores. Here's where we are today. Sorry, bad angle. Here. Not so good. The other part of the graph that I want to point your attention to is the red. So if we look at what we know about the CO2 concentration in the atmosphere, and we compare that to the temperature, there's a relationship. As your CO2 goes up, so does your atmospheric temperature. So the question is, now that we have this red dot or that blue dot exceeding the levels that we've experienced in the last 800,000 years, what's going to happen to that red line? And that's what we're concerned about with climate change. I'm going to go ahead and skip this one because I mentioned this. If you want to learn more about some of the other chemicals, let me know. Otherwise, I'll spend too much time on this. You want to just put through my innovations. But you can see on the graph, all these things are rising, just like CO2 is. Okay, so how certain are we that climate change is due to us? We're about 99% certain. These are the three main sources of these fossil fuel emissions and CO2 and other chemicals. So we have fossil fuel consumption, our cars, our factories, and then we have deforestation. So what's going on in the Amazon with farmers burning into the forest. All of that carbon that's stored in the tissues of the plant and in the soil, when you burn it, goes into the atmosphere. So instead of the rainforest being a sink of carbon and a storage of carbon, now we put all of that carbon into the atmosphere in the form of CO2, and that's a problem. We also have livestock production as well. So not only the food that we grow to feed the cows and the pigs and the lambs, but we also have a lot of methane production from those livestock, and methane is a greenhouse gas. This is an animation here. I just wanted to illustrate the extent of climate change. So this is another temperature anomaly graph from NASA. So if you want to just hit play here, the hotter colors are hotter than normal, and then the bluer colors are colder than normal. And so this is a model from the 1800s. I believe it goes through 2017. So now we're in the 1950s. This is the 1960s, 70s. Here's the 80s. Here's the 90s. Now we're in the 2000s. Pretty shocking, huh? Yeah. Okay, and then there's another one more figure to illustrate. So what this is showing you is the change in temperatures. And this is based on the different regions of the world, different continents, including Oceania. And then we have all of the countries within those regions that are listed there. So it's showing you the temperature anomalies over time globally. And just another way of looking at these changes. Hopefully there's not a commercial, it's a YouTube video. So again, blue is colder than normal, red is hotter than normal. Yeah. So what are the consequences of all of these extra greenhouse gases? I'm going to focus on CO2, because like I said, that's 80% of the identified problem. So we have increases in global temperature. Those are going to have direct impacts to the oceans. That influences sea level rise. One of the consequences of sea level rise is something called saltwater intrusion. And so that's when, as you have the rise in sea level, especially here in Florida, our aquifers are very close to sea level. And a lot of our aquifers are unconfined, and the bottoms of them are just this very delicate balance between freshwater and the underground seawater. And you get a little bit of a break in that halocline, the difference between the saltiness of the water, your aquifer gets contaminated with salt water and it becomes undrinkable. And then you have to put something called a desalination plant to get the salt out of it so we can drink it. And those are very expensive. Those rely on fossil fuels. And so you contribute to the problem that way. So saltwater intrusion is that pushing of the ocean into our aquifers, but also into our rivers, also into our estuaries, also into our retention ponds, also into our lakes. All of it is connected. And so when you have that saltwater coming up, that's going to have those effects in both freshwater and saltwater and those estuary type ecosystems. We also have changes in thermal expansion. So when you look at water, molecules of water, and when you increase the temperature of molecules of water, they begin to expand. You guys have experienced this. You've done this experiment in your kitchen. How many people cook pasta? You put that pot on, you put a little bit too much water in that pot, it boils over, right? It's not that more water got into there, it's just the molecules of water expanded, and you get that thermal expansion. So if you have cold water in a container, it has a lower volume. Additional expansion of the water due to those changes in the chemical properties. There's some elements of ocean stratification. It's kind of complicated. I don't have the time to get into it, but that has really important consequences to the oxygen and the nutrients that are in our water, causes fish kills and things like that. So I can talk a little bit more about that on the one-on-one. I'm going to touch briefly on the tropical cyclone activity because I think that's important for what we experience here in Florida. We also have changes in ocean chemistry. Yeah. Okay. And all of these things, these chemical changes, these physical changes, then have consequences on the biology and the ecology. So here's another animation. This is showing the extent of sea loss at the North Pole. So what you're looking at here, if you want to go ahead and press play, the lighter colors are the older sea ice on the North Pole. And then the gray colors are the annual sea formation. So when it gets to winter, the sea ice expands, and then in summer it melts back. So I want you to look at what's happening to the white ice as well as to the gray ice. One of the things I want you to keep in your mind too as you're watching these changes is that the North Pole and the South Pole are covered in this ice, and ice is very reflective. If any of you have ever been able to go out in the snow, you come from your house outside, you open the door in the morning, it's like, blinding light, because that ice reflects energy. And remember that I said 30% of the energy that comes from the sun gets reflected off of our atmosphere, off of our sea ice. And so the more ice we lose on the planet, the more energy is absorbed into our atmosphere versus reflected back out into the atmosphere. And that creates a positive feedback where we get more and more warming. So here we are in 2009 and 2010, 2011, 2012. And you see how much open ocean is now available during these warmer months. We now have sailboats that are able to go through the North Pole. So polar bears, harbor seals, all of those beautiful creatures, this is their habitat that is shifting. I wanted to touch briefly on the impacts to tropical cyclone activity. So one of the things you might see in the news is something called tropical cyclone heat potential. It's a temperature within the water that meteorologists have identified that fuel hurricanes. And so that tropical cyclone heat potential, if you want to click, is that warmer upper layer of water that provides fuel for hurricanes to form. And the hotter the water is, the more energy for those hurricanes. And so the tropical cyclone heat potential is what depth of water has reached this critical temperature of 78 degrees. And with climate change, the ocean is getting hotter. So the more area of the ocean has that tropical cyclone heat potential, and the deeper layer of water that is hot as well. And so all of those things we predict are going to lead to increased numbers of hurricanes, as well as hurricanes that have greater strength, more category 4 and 5 storms. So one of the things you will see a lot in the literature is, or in the news even, is that we can't really say this is because climate change. Scientists are very picky. If we don't have the data, we don't like to make overly grandiose statements. The problem with hurricanes is that we don't have a long historical record of hurricanes. We have sort of vague historical notes going back, even China, going back, several centuries. But we don't really know much about hurricanes going back into the past. So we have a very short time scale of data, and it's not very accurate to make predictions off of a very small data set. So we think all of the math and the science makes sense that this will happen, but we can't conclusively say that until time goes on. So be frustrated with us, but we have standards. Sorry. Okay. Here's our stronger hurricane. Okay. So another physical change is ocean acidification. So when you have carbon dioxide in the atmosphere, it dissolves into ocean water and fresh water. And when you have a molecule of water mixing with a molecule of CO2, it actually rips the hydrogen off and it produces a hydrogen ion that is positively charged. If you guys remember back to chemistry, you learned about pH, and pH is calculated as a ratio of hydrogen ions and hydroxide ions. So the more hydrogen ions that you get, the pH begins to drop and it becomes more acidic. We are actually seeing these changes in ocean acidification in estuaries across the world. It's happening. We know that it's happening. There's countless studies that are coming out showing what are the impacts of these changes in those hydrogen ions to marine organisms. So I got a couple animations. One other thing I'm not going to touch on is carbonate ions. The other consequence is that the calcium carbonate that corals and mussels and barnacles and things build their shells with is now no longer available in the water. So not only do you have the shells dissolving because of the change in pH, but it's now energetically costly for them to make their skeletons and make their shells. So there's been overall a 26% increase in the amount of hydrogen ions, and that's led to a noticeable decrease in pH. You could click through a couple of these, please. Okay. So I studied the seahorse, and I only have like a minute left. Go ahead and click a couple of slides. So when we look at something like a seahorse, we have all of these different things that we know temperature influences. With ocean acidification, we know that all of these other elements are there as well. You want to click? That impacts the biology and the ecology of the seahorse. But then you also have the entire ecosystem that the seahorse interacts with. So if you click, we got the zooplankton that they eat, and then what the zooplankton eat is the phytoplankton. Then seahorses live in the seagrass beds, and all of these organisms are also impacted by changes in temperature and the chemistry of the water. Okay. And then when we look at coastal ecosystems, this is just a list of all the wonderful, beautiful places that we love here in Florida and beyond. So if you want to click again, I just did that one. And then click one more time. These ecosystems experience a lot of natural disturbance. They have hurricanes, they have, if you look at the sandy beach, they got high tide and low tide, and those waves are crashing, animals have learned to either move out of these areas if they can't tolerate it, or over time, those organisms have the ability to adapt to those natural disturbances. But then when we look at all of the types of human disturbance that we put onto these ecosystems, nutrient addition, plastics, oil spills, disease, chemicals, overharvesting, destructive practices, invasive species, marine structures, human encroachment, and climate change. The question is, if these populations have the ability to adapt to another level of disturbance. And so we call that a term called resiliency. How much built-in resiliency do these populations have to rapidly adapt to these extra disturbances that we're facing? So one of the things I want to leave you with in terms of hope is that there is resiliency in these systems. There is a lot of repetition in these marine systems. You have species that can, when one species disappears, another species can come in and take over some of the function of what that lost species is. So climate change is happening. We've kicked that snowball down the hill. There are going to be shifts, there are going to be changes, but not every species is going to disappear. There are some species that like the changes. They're opportunistic. They might even have qualities of an invasive species. So the things that are normal in our mind may not be what's normal in the future. And so it's just a question of if we can preserve and protect the things that are important to us and try as much as we can to slow that snowball that's coming down the hill and not melt it. Let's not melt it. Okay, and I want to just click through, there's one last slide I'm going to leave us with in terms of hope. These are all the ways that climate change influences these habitats, these species. So what can we do? I'm going to leave you with this quote. So it says here, I used to think that the top environmental problems were biodiversity loss, ecosystem collapse, and climate change. I thought that with 30 years of good science, we could address those problems, but I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with those, we need a spiritual and cultural transformation. And we as scientists don't know how to do that. I thought that was very true. Especially with, what we're experiencing now with our political climate. We're blue versus red, right? I was reading a paper that had come out that was talking about how do you bridge the gap? How do you talk about climate scientists to people that are just tired of hearing about climate science? And one of the things that they said is that you can be the representation in your community. The actions that you take as an individual provide that anecdotal evidence that people need to say, oh yeah, I saw she's got solar panels. I saw that cut down her, her heating bills. I saw that they planted native species in their yard, and that led to less, fertilizer you had to put on. You can be the example to show people how this works, because a lot of times it's that personal connection that changes people's minds. The other thing is finding common ground. There's so much that divides us. We are all sons and daughters. Some of us are mothers and fathers and brothers and sisters. if we find the things that make us the same and connect us, and if you can earn somebody's trust as a person, then you can open up these conversations about these harder to digest topics for some people. But if you come at them with, you got to do this, you got to do that, we're not perfect people. I'm not a perfect, citizen of the world in terms of, I know all of this stuff, and I used a straw at Starbucks this morning. We all make mistakes. We all have to deal with the way that our society functions at this point. And it's a challenge to do everything right. And I think we need to respect that and work together as a community at all of these different levels to see the changes that we need to make. So that's my 2 cents. But thank you so much for your time. Thank you for inviting me to your congregation and seeing your service. And I'm happy to answer questions when we have time. But thank you so much.